Here's a theorem you might already be aware of, the triangle sum theorem, that states that the sum of the measures of the three angles of a triangle is 180 degrees. And the triangle sum theorem can be used to prove this theorem, known as the no-choice theorem. If two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. The two theorems together can also be used to show that if you know two angles of a triangle, you can add them, subtract from 180, and get the measure of the third previously unknown angle. And now here's a theorem that we can prove using those first two theorems. This is the AAS theorem for triangle congruence. If there exists a correspondence between the vertices of two triangles, such that the two triangles and a non-included side of one are congruent to the corresponding parts of the other, then the triangles are congruent. While some of our statements of congruence for a pair of triangles were postulates, this one can be proved. So it's the AAS theorem. And here's the setup. We'll mark out our angles to show that we're given two pairs of congruent angles and a not included side. We're given angle B and angle Y, angle C and angle Z. And here's the pair of sides, AC and XZ. Our strategy is that we'll use the no-choice theorem to figure out that angle A is congruent to angle X. And then you can see we have an angle-side-angle situation between the two triangles, and we'll use that to prove the two triangles congruent. So now that we've laid out our strategy, let's write the reasons. We'll state the first given, and that's a pair of angles. So we put the little letter A next to reason 1. And then we state the given that states that a pair of sides are congruent and write out the letter S next to that reason. Then we state the third given that another pair of angles is congruent. And then we find the third pair of angles congruent by the no-choice theorem. And that's the pair of angles that's going to complete our angle-side-angle statement of congruence for the two triangles. So now we'll state that the two triangles are congruent, and of course the reason is ASA. So we've used the postulate ASA as an important reason for the proof of the theorem AAS. Let's summarize the theorems and postulates we've used to prove triangles congruent. We start with SSS, presented by some textbooks as a postulate, but there is a proof for this one, so it can be presented as a theorem. SAS is a postulate that works. ASA is another postulate that works. AAS we just proved, and while the first three are the same backwards as they are forwards, AAS could also be written as SAA. I think it's commonly written alphabetically AAS, but either way is fine. Both mean two pairs of congruent corresponding angles and a pair of congruent non-included sides. And then we know that two triangles can have all three angles match, but they're not necessarily congruent. They can be congruent, but it's not required they're congruent, and in fact, they're known as similar triangles. And we'll talk more about similar triangles in later lessons. So the one combination we haven't addressed is SSA, which means two sides and one of the non-included angles. Of course, SSA, written alphabetically, is ASS, and it turns out it doesn't work, so the joke is if you use ASS as a reason to prove two triangles congruent, you've made one out of yourself. But let's look at why SSA or ASS doesn't work. We start with a given angle. The black rays represent sides of the angle. And then we're given one of the three sides of the triangle, and we mark it off on one of the sides of that angle. Then we're going to be given another side of the triangle. But we're not allowed to mark it off on the other side of the angle because this potential theorem or postulate says that the angle is not the included angle between the two given sides. So we have to put the side like this, and we can do that, and we've made a triangle. And there's our triangle. But we can also take that side and put it in like this. That gives us this triangle. In this case, two different triangles can be formed given two sides and a non-included angle. So we can't use SSA as a theorem or a postulate, because in order for it to work, it has to work in all cases. Well, here's another case we could examine. We're given an obtuse angle and two sides which are not both sides of the obtuse angle. Well, if we put the big one down there and then we put the smaller one there, we can't even make a triangle. So that can't even happen. So we'll switch them and put the smaller one there. Then we can put the bigger one in there, and we can make a triangle. And it turns out, if our given angle is an obtuse angle, there's only one triangle that can be formed, provided one of the two given sides is the longest side of the triangle. However, I know of no special theorem or postulate for this special case. But there is a theorem for this special case, the right angle case. So our non-included angle is the right angle. We already know we can't put the large one there because the large one has to be opposite the right angle. So there's our smaller of our two given lengths. Our larger length goes there, and that becomes the hypotenuse of the right angle. And that's the only triangle that can be formed. And that's going to give us a postulate. It actually can be proved as a theorem, but one of my textbooks calls it a postulate, the other a theorem. I have a proof for this, so you can call it a theorem. My proof is not the same as the one given in my second textbook. But first, let's state it. If there exists a correspondence between the vertices of two right triangles, such that the hypotenuse and a leg of one triangle are congruent to the corresponding parts of the other triangle, the two right triangles are congruent, and we call that HL. So we use HL for hypotenuse and a leg of a pair of right triangles. And my proof for this theorem involves this theorem that you may have already heard of, the Pythagorean theorem. The sum of the squares of the lengths of the legs of a right triangle is equal to the square of the length of the hypotenuse. So if you're given the length of a hypotenuse and the length of one of the legs, you can use this equation to solve for the length of the other leg. And once you know the lengths of all three sides of a pair of right triangles, you can prove congruence by side, side, side. So the HL theorem or postulate can be proved using the Pythagorean theorem. Well, in this lesson, we looked at the triangle sum theorem, a theorem you may already have been aware of. The sum of the measures of the three angles of a triangle is 180 degrees. We also looked at the no-choice theorem. If two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. We used the no-choice theorem to prove the AAS theorem. And another familiar theorem that you may have already been aware of, the Pythagorean theorem. The sum of the squares of the lengths of the legs of a right triangle is equal to the square of the length of the hypotenuse, or simply stated, a squared plus b squared is equal to c squared. And then we looked at and proved the angle-angle side theorem. We also looked at a postulate that could also be proved as a theorem, the HL hypotenuse leg postulate. And to summarize, the reasons that can be used to prove a pair of triangles congruent, we have the SSS postulate, which can also be proved as a theorem, the SAS postulate. And by the way, some textbooks, when right triangles are concerned, instead of saying SAS, they say leg-leg, because the right angle is the included angle in SAS. So while not all textbooks use leg-leg, many do. So if you see LL, that stands for leg-leg, and it's used to prove a pair of right triangles congruent if you know the lengths of the legs of both triangles. Then ASA is a postulate that we had looked at in a previous lesson, and AAS was introduced and proved in this lesson, and HL was also introduced and proved in this lesson.